In this problem, we're asked to compute the surface area of a sphere of radius a, and we're asked to do this as thinking of this as a parametric surface. So to do so, let's recall that for a parametric surface S, the area of this surface S, so in this case S is the sphere, the area of S is just a double integral over this surface of 1 ds, okay, and so this is perfectly fine as a philosophical formula, right, conceptual formula. But to compute this, how do we do it? Well, actually what we do is we have to define a parametrization, a certain kind of parametrization, so some kind of vector function, R, which takes a domain, two-dimensional domain, and maps it to the surface, and it has to do so in such a way that it covers the surface exactly once, right? But in doing so, what we end up with is over here we're going to have to define some domain D in the parameter domain. We integrate, actually, to compute the surface area, over the parameter domain D, we integrate the length of the normal vector, which we'll compute over here, okay, the normal vector, dA, back here in this domain. So ds, the surface area element here, is equal to the length of the normal vector times dA on the surface, okay, pulled back to the parameter domain. So what we have to do, the first step before we can compute this surface area, is we need to think of a way to parametrize this sphere in such a way that the parametrization is smooth. We never have any breakdown of the normal vector field, okay, and also that it covers the surface exactly once. And we know how to represent a sphere in many different ways, but one way that we've studied recently is spherical coordinates. Okay, so for us, let's remember how the spherical coordinates work for us on this example. Let's do that, and then we'll be able to write down a formula for our parametric function r here. So the first thing is we just want the sphere, okay? So the first thing we need to do is go out to the surface. So we need to get out here to this radius, right? So we're going to fix our rho, our radius in the spherical coordinates, equal to a. Now, the way I've drawn this, you might be thinking in your mind, you fill out this entire segment, and that's what you would do if you're going to fill out a solid sphere or a ball, but that's not the question here, right? We only want to know the surface area of this surface, so we just go out to radius a and we stay there, okay? We get out there, we stay there. Once we are out at this point, now we need to somehow build the sphere, right? And so the way we do this in spherical coordinates is from here, we rotate in this direction, right, down from the positive z-axis, and we get that our phi varies from 0 to pi. All right, so there's our first parameter. So over here in our domain space, I'm going to write phi, and phi is going to vary from 0 to pi. All right, and so there's our first, like I said, our first parameter. That's going to trace out this segment, arc segment. Once we have the arc, we need to fill out the sphere. How are we going to do that? Well, we take this arc and we rotate it around in the XYZ plane direction, and there's our angle theta. This one varies from 0 to 2 pi, and that right there is our second parameter. So in the parameter domain, varying from 0 to 2 pi, we see that our parameter domain looks like a rectangle, actually. So our parametrization turns a rectangle into a sphere, and it does so in a way that is smooth, okay? Smooth means that the normal vector never gets zeroed out, and it's continuous. It's got all nice properties, right? This normal vector. So this is what we're going to integrate over, this domain D over here, which is just a rectangle in our phi theta plane. Okay, so the next step is we actually need to write down a formula for the parametrization, and this formula comes from just utilizing spherical coordinates, okay? Just writing down spherical coordinates and working with them. So let's come over here and do this. Our spherical coordinates, remember, are that x is equal to rho sine of phi cosine of theta, y is equal to rho sine of phi sine of theta, and z is equal to rho cosine of phi, okay? But we're not using all the spherical coordinates. We want theta and phi to vary, but we have fixed our rho equal to a, right? So now we go back through and we just swap out the rho for constant a, and our parametrization is then our r as a function of phi and theta in this order. We've talked many times about why this order is correct, is now given by a sine of phi cosine of theta, a sine of phi sine of theta, and then a cosine of phi. So there's our parametrization right there. To build the normal vector, remember our vector nu, this is going to be equal to the cross product of the partial derivatives. So this is r sub phi crossed with r sub theta. These are our two parameters now, right? And this is, again, the proper order here to get this thing to be outward pointing, which is going to be important as we move forward. Not super important on this one because we're going to take the length, but it is important. So r sub phi, this is the phi partial derivative of this vector function. So the derivative of sine is cosine. Derivative of cosine is negative sine. So what do we end up with? A cosine phi cosine of theta, a cosine of phi sine of theta, and then minus a sine of phi. Okay, so there's the phi partial derivative. We now do the same thing with the theta derivative. So same deal, we just go through. By the way, there's no thetas in this last component, so that's going to be 0, right? But as we go through, this is going to be what? Minus a sine of phi sine of theta, positive a sine of phi cosine of theta, and then 0. And at this point, we need to take the cross product of these two vectors to build our normal vector nu. Remember, this nu is a Greek letter. So we need to take the cross product, and we end up with nu is equal to, I'm just going to kind of symbolically do it here, 0 minus a negative. So this is plus a squared sine squared phi times cosine of theta. That's in the first component. The next component, it's going to be this times this. These two minuses cancel. Here we have a squared sine squared phi times sine of theta. And then finally, we have these two components, right? So in this last component, it's going to be more complicated. This one's going to be a squared sine of phi cosine of phi times cosine squared theta plus a squared, plus because of minus minus, a squared sine of phi cosine of phi times sine squared theta. So I'm computing the cross product here. And at this point, we notice we've got this, and Pythagorean identity, right? So that one's going to simplify. And we now need to compute the length of this, because what we have to integrate is the length of this normal vector nu at this point. So this has been simplified. What do we need? We need the length of the vector nu. This, I'll write length squared. We'll take the square root at the end. Okay, we need a square root, right? But we need to sum up the squares of these terms. So let's just look at the first couple. We have a squared sine squared phi times cosine squared theta, that whole thing squared, times cosine squared theta, plus a squared sine squared phi times sine squared theta, plus a squared. So what do we have left here, right? So I don't need these parentheses here. So a squared squared, so that's a to the fourth, right? Be careful. So a to the fourth sine squared phi cosine squared theta. And that's it. Again, we see Pythagorean identity. This happens a lot when you use spherical coordinates. I forgot a square here. But we see these two terms are the same. These two terms make a Pythagorean identity. I switch the colors around. But this whole thing now just becomes a to the fourth sine squared phi sine squared phi plus a to the fourth sine squared phi cosine squared phi. Notice what I did here. I wrote sine squared squared as just two copies. And again, the reason is because we see this term. We see Pythagorean identity. And the length squared of our normal vector becomes a to the fourth sine squared phi. All right? And when we take the square root, we get that our normal vector is just a squared sine of phi. Okay? And so this is now exactly what we need to integrate up. A squared sine of phi, and let's do it. So this is now the integrand of our area integral. Again, we go back up here. Area, this is what we're integrating. We're integrating over d. This d is a rectangle, right? So this integral is actually going to be pretty straightforward. The boundaries are just 0 to pi in the phi direction, 0 to 2 pi in the theta direction. So it's a nice rectangular boundary back here in the parameter domain. And so all this tells us that our surface area that we're looking for of our sphere is given by double integral 0 to 2 pi, 0 to pi, so I've got phi on the inner integral, of this constant a squared sine of phi d theta. All right, and so this is separable. A squared is a constant. The theta is just, the integrand is just a 1, so that's just going to be 2 pi. And then the thing we need to integrate is 0 to pi sine of phi d phi. Okay, and so again we have now here 2 pi a squared times antiderivative of sine is minus cosine of phi applied 0 to pi, 2 pi a squared times, this is going to be negative negative 1 minus a negative 1, so 1 plus 1. And what we end up with is 4 pi times the radius squared. And that is, by the way, we knew the answer to this one, right? That is exactly what we should have gotten. We did get it. So this is the surface area of a sphere when regarded as a parametric surface.